So today we're very pleased to have invited Krishna from UC Davis to visit us. Krishna is an assistant professor in the Department of Statistics at UC Davis. His recent research interests include stochastic optimization and sampling theory and computation with tensors, higher order interaction analysis, and theoretical analysis of kernel methods. His research is supported by Facebook PhD fellowship, CDAR, and NSF grants. And without further ado, let's welcome Krishna.
Thanks, Ian, for the introduction. I'm delighted to talk about some of my recent work on zeroth-order optimization here at UCSD seminar. I wish it could have been in person, and it would have been nice to visit you guys in person, but nevertheless, here we go. So this talk is based on two of my current works. One published in Foundations of Computational Math, and the other one currently under review. The first work is in parts joined with Saeed Ghadimi at University of Waterloo. And the second work is with Jiaxiang Li and Shiqian Ma, who are both at the math department at UC Davis. All right, so the problem that we will consider in this talk is the following optimization problem, or stochastic optimization problem to be more specific. So you're given an objective function little f of theta, which is written as expectation of some capital function, capital F of theta and another random variable x. So this little f of theta is basically the expectation of this capital F function, right? And there's also a constraint set theta, which could also be the entire subset, entire set RD, in which case the problem is unconstrained, or you could have it to be a closed convex subset of RD as well, right? So this is the standard stochastic optimization setup, and a lot of problems that arise in statistics and machine learning could be cast under this framework, and it's widely applicable in some sense, right? So the focus of today's talk will be on a setting called as the zeroth order setting. So the typical assumptions that are made on the availability of information to solve this optimization problem goes as something like a zeroth order oracle, or a first order, or a second order oracle. And as the name suggests, zeroth order oracle means that you only have access to potentially noisy observations of the function f of theta. If you're talking about the first order setting, you would also have access to the gradient of these functions, potentially noisy again. And as the name suggests, if you have second order oracle, you would also have Hessian information and so on and so forth, right? And our focus today will be completely on the zeroth order setting, where you only have access to the noisy function evaluations, right? All right, so just to give a little bit of the history of the problem, so this paper in 1951 is the famous SGD paper by Robbins and Monroe. And following year, in 1952, the same September month, Kiefer and Ulfowitz came up with arguably the first zeroth order algorithm for finding the maximum of a regression function. And both were published in Annals of Mathematical Statistics. And the motivation for the second paper, this paragraph is from the second paper. So the authors tell that the motivation came from this interesting paper by Robbins and Monroe, which is the SGD paper, right? And finally, the authors also tell something like the statistical importance of this problem is obvious and need not be discussed. I wish I could also write something like this for the introduction and get away with it in these days, right? So since the publication of these papers and several subsequent works, this field of zeroth order optimization has itself become a substantial field in itself, and it goes by various names, including black box optimization, evolutionary strategies, Bayesian optimization, random search, and banded convex optimization. This banded convex optimization is arguably very well known in the machine learning community because in this case, the constraint set here is just a finite set with a countable, no, it's like exactly finite cardinality set. So, and it also goes by the name of multi-armed bandit and so on and so forth, right? And it has been studied in various fields and their intersections, including machine learning, statistics, operations research, and applied mathematics, right? So our focus today will be, so recently this problem has also been studied in statistical machine learning community, mostly due to its application in reinforcement learning and hyperparameter tuning. Our focus today will be a little bit, at least for motivational sake, we would be talking about this hyperparameter tuning problem. So here the problem is, like, imagine you have even like a simple ridge or lasso estimator, and you want to set the tuning parameters, or more, as a more complicated example, you have like a deep neural network or some black box prediction algorithm, and you want to set the tuning parameters or the knobs of those algorithm. And your goal is eventually to get a good test set accuracy or generalization error, right? So you want to have you want to tune the knobs to get the best test set accuracy or the minimum test set accuracy, right? So I mean error. The problem would then be you would never have, in most cases, an analytical relationship describing analytical form for describing the relationship between these tuning parameters and the prediction error for complicated prediction algorithms, right? But what you can do is you can set these tuning parameters to various values and empirically or through simulation observe what happens to the test set accuracy, right? So in that, if you view that, if you view this, I mean, this process could be viewed exactly in the setup that we are working with, because you want to minimize the hyperparameters. You want to minimize the test set error which is viewed as a function of these hyperparameters, but you don't have an analytical relationship between them. So you set the tuning parameters to various values, and then you get the noisy evaluations of these functions, right? So this exactly falls under our category of having only zeroth order information while optimizing a function, right? So that's why it has gained popularity recently in the machine learning literature, or that's one of the reasons why it has gained popularity, right? So the most popular approach that works well in practice for performing zeroth order optimization is kind of so if you go back to this slide, the problem of first order optimization or second order optimization has been very well studied in the recent past. I mean, probably in the last few decades, right? So the most naive or the easiest approach that also works well to do zeroth order optimization is actually to estimate the gradients and Hessians through these objective function evaluations, or based on these objective function evaluations. And then you just employ those estimated gradients and Hessians in standard first order routines or second order routines, right? So this way you're kind of leveraging the huge amount of work that has gone into developing extremely efficient first and second order algorithms, and you're not losing out on anything, because you kind of estimate your gradients and Hessians from the zeroth order information, based on the zeroth order information, right? So that's a strategy that kind of works very well in practice. And the way to measure the performance of your algorithm in zeroth order setting is through this oracle complexity, which is just the number of function calls you need to get an epsilon accurate solution. But what I want to, I'll be precise about the definition in a minute, but what I want to highlight is that because you're actually, let's stick to the first order method, right? So if you're thinking of a first order method and you're estimating the gradient using the zeroth order information and then plugging that into this first order method, the difference between the oracle complexity of a first order method and the zeroth order method would be, there would be an additional, at least additional linear factor in D, the dimensionality of the problem, right? So that is the main difference that you would have by doing this approach. And it is also known through lower bounds that this linear dependency in D could not be cannot be avoided without further assumptions, right? So that's kind of like a brief summary of this zeroth order optimization literature. And most recently, there's this paper by Nosedal's group, which compares this approach with various other approaches that have been developed to do zeroth-order optimization. And the tone or the conclusion of that paper more or less suggests that the progress in this community would have been much faster if we kind of adopted this methodology much earlier than we did, right? So that's kind of like the rough tone of this paper, right? All right, so now that we are going to focus on this approach where you estimate the gradients or Hessians from the zeroth order information and then use it in standard routine first order or second order methods, the problem eventually boils down to estimating derivatives, right? And that is done through the Stein's identity, which is very popular in statistics literature. So let me explain what I mean by that. So let's consider first a simple problem where you have no noise. So you're given access to a function f of theta in form of function evaluations, which are exact. So you know the exact value of the function at any given point, theta 1 or whatever. So the problem is now to estimate its gradient, right? So what you can do is, in a paper by Nesterov and Spokane, they showed that you can define a closely related function, this f nu of theta, which is nothing but a perturbed version of f of theta. So basically this f nu of theta is just expectation with respect to u of f of theta plus nu u. So you're just basically taking, and this u is basically just a standard Gaussian random vector, right? So you're just taking a perturbation in a random Gaussian direction and then taking the expectation. So this is the smoothed function of the given function f, right? And Nesterov and Spokane showed that you can estimate the gradient of this function, the f nu function, using something like this, right? So the thing to notice here is that this is just a function evaluation, this is just a function evaluation, this is just the scalar, and this is a vector. So this expectation here is going to give you the gradient of this function. And furthermore, what we really need is the gradient of this function, but what we have obtained here is the gradient of a closely related function. And the reason why I tell it's a closely related function is that the distance between the gradient that we need and the gradient that we have in some norm could be bounded in this particular manner. And it could be controlled basically by picking this parameter nu, the smoothing parameter, right? Indeed, this idea is not first proposed originally by Nesterov and Spokane. Various versions of this idea was floating around in the literature as early as like 1983 in Nemirovsky and Yuden's book, and also there's a paper by Polyak and Chivakov, who also had a related idea, and then Spal and various others literally had this idea. But only recently, Nesterov and Spokane showed non-asymptotic oracle complexities for these methods, right? And these sort of bounds were developed by Nesterov and Spokane, right? So this kind of the point is now, why does this provide a gradient of this function, provide the gradient of this function, right? And it could be justified simply by Stein's identity, right? So if you have a Gaussian vector in d-dimensional Euclidean space, Stein's identity tells that for any function for which these expectations are well defined, let's say smooth enough functions, the expectation of u times g of u is going to be the expectation of gradient of g of u, right? So this is a identity due to Charles Stein for characterizing Gaussian random variables. And the reason, so one can say that this identity just holds regularly by integration by parts argument. But the reason why there's a name for this identity is that Stein showed that if this identity holds for a large class of functions, then the corresponding random variable is could only be the Gaussian random variable. So it provides an if and only if characterization for Gaussian random variable, which is why it's called as a Stein's identity. However, we only need one direction, so to speak, right? So so given this identity, if you just set g of u to be this f of theta plus nu u, the perturbed function without the expectation, then you can immediately set this g of u to be f of theta plus nu u in this expression, and you'll notice that you can have you can add for free this f of theta parameter, this term f of theta, because u is a zero mean Gaussian random variable. So by linearity expectation, this is just zero. So I'm just adding f of theta for free. So this is basically by Stein's identity nu times expectation of gradient of f of theta plus nu u, right? So this pretty much tells you that this estimator proposed by all these people and analyzed by Nesterov and Spokane is just an instantiation of Stein's identity, right? So this relationship also implies that we can basically estimate the gradient of f nu only by function evaluations, right? So indeed, if you just go to the Stein's identity definition, you have just zeroth order information on one side and the first order information on the other side. So in a way, Stein's identity is kind of like readily applicable for estimating the gradients based on just function values. You just need to set up the function properly, right? Any questions so far? Maybe I'll pause briefly. All right, so if not, let's proceed. So basically, I introduced this zeroth order gradient estimator for the deterministic setting or the non-noisy setting. The same idea also extends for the stochastic setting. So where you observe the functions with noise, you just have this g nu of theta as the point, x is your randomness in your data and or your noisy evaluations, and u is your Gaussian random variable or random vector. So you just need to do the noisy difference here and then multiply that with a u vector, right? And you can immediately show that in this noisy setting as well, this expectation of u, expectation with respect to u and x of this gradient estimator is going to give you this del f nu of theta. So this is an unbiased estimator of the gradient of this smoothed function in the noisy setting, right? All right, so now I'll talk a little bit about the evaluation metrics and the existing results in the literature for these evaluation metrics, right? So we say that theta bar is a solution. So we are given a solution theta bar and an accuracy parameter epsilon, and in the convex setting, we measure the objective function evaluated at the solution minus the objective function at the minimizer. So theta star is the minimizer of the solution optimization problem. So we want this metric to be less than some epsilon. So that's what we call. So we call in this case, if theta bar satisfies this condition, we call theta bar as the epsilon optimal solution of the problem, right? And in the non-convex setting, there are various ways. In the general non-convex setting, without any further assumptions, there are multiple ways to define optimality. Of course, obtaining global solution in a non-convex setting might require exponential dependency on the dimensionality and so on and so forth. So what we could at least hope for at the bare minimum is we converge to some stationary point. And the common notion is to use this first order stationary solution, which is given by the gradient size in some norm being less than epsilon, right? And if a theta bar satisfies this condition, we call it as an epsilon stationary, first order stationary solution for a non-convex problem, right? So what is known in the prior literature is that for the convex case, recall that the oracle complexity is the number of function evaluations, right? So the number of function evaluations to get an epsilon optimal solution in the convex case is d over epsilon squared, and the number of function queries you need to get a first order stationary solution in the non-convex setting is d over epsilon to the 4, right? So these are the two oracle complexity results that are available in the literature so far, right? And the corresponding first order results would read like 1 over epsilon squared and 1 over epsilon to the 4, right? So these are the two conditions. I mean, these are the two results that are widely known in the zeroth order setting, and the presence of this additional factor d is the difference between the zeroth order and the first order setting that we try to address in this work, right? So because of this presence of this additional factor d, in comparison to the first order methods, zeroth order methods are like suffer increased oracle complexity, right? So for high dimensions, zeroth order methods are difficult to make them work. It is difficult to make them work, right? So our goal totally today would be on getting oracle complexities which reduce this d factor, some sort of a sublinear rate in d, or uh, um, something along those lines, right? That would be our goal today, right? All right, so as I told before, we also have a lower bound in the zeroth order setting. So this d can't be avoided without any further assumptions. So we are going to make some assumptions which make sense in practice. So the first such assumption is what is called as the sparse key assumption. So what we are going to do is we are going to assume that the function f, which is defined from Re to R, is S sparse, in the sense that it is going to depend only on S of the d coordinates, right? So recall that we don't analytically have the form of this function f. You only have the objective function evaluations. So we don't know which of the S coordinates among the d coordinates the function depends on, right? So basically there is just some unknown S coordinates out of the d coordinates on which the function depends on, right? So if this assumption is true, one can immediately see that the gradient vector at any point will also be the L0 norm, which is just the number of non-zero entries in your vector. That also will be upper bounded by S, and the gradient of the smoothed function will also be upper bounded by this S parameter, right? And this assumption is motivated by this problem of hyperparameter tuning as well. So if you can think of this as a idealized example perhaps. So for example, in a deep neural network problem, you might have like thousands of tuning parameters that you need to manually set, but only a few of them may actually matter to get good generalization performance, right? So not all of them is going to matter, right? So that's kind of like the rough motivation for this sparsity structure on the function being optimized, right? And apart from that, because it's a general non-convex function, so we can allow f to be generally non-convex. So this is a gradient smoothness assumption we make, which is pretty standard in almost most optimization papers. This could be relaxed. However, we would not get into this in this talk, right? So for at least for the sake of this talk, we assume that the function is gradient Lipschitz, which means that if you measure the gradient at 2 points, it is upper bounded by some constant times the change between the 2 points, right? For some norm in RD, right? So since the publication of this work in archive, since putting this out in archive, several groups have also looked at relaxing these assumptions and things like that. So in this paper here, they looked at the gradient of some practical problems. So for example, this ImageNet adversarial attack problem. So let me explain briefly about this figure. So basically, this is a 1,000-dimensional problem. So the gradient, there's going to be like 1,000 coordinates for the gradient vector. So they have randomly sampled the objective function at 100 points, and they calculate the gradient at those 100 points, and they sort the coordinates of the gradient, right? So basically you can see that almost when you go to like 200 top 200 coordinates, the magnitude literally goes pretty close to 0 of these the gradient coordinates, and around like 400 it's kind of like negligible. So basically this kind of is a relaxed sparsity assumption. So here in our previous assumption, we assume that there are exactly s of the d coordinates which are non-zero, and then the remaining are 0. But here this assumption could, or this practical setting could be thought of as like just like a weak sparsity kind of an assumption. Instead of L0 sparsity, it's kind of like a weak sparsity assumptions, right? And indeed, our results could perhaps be extended to this weak sparsity setting, but we haven't done that in the paper. So for this talk, we would just focus on the exact sparsity setting, right? All right, so now we also need a couple of other assumptions on the oracles that we have. So firstly, we assume that at each point that we query, although our function evaluations are noisy, the expectation of the function evaluation is unbiased. So meaning that if we take the expectation of this the random function or the noisy function, you get the little f of theta, right? And similarly, although we don't actually observe the gradient, we just assume that the function evaluations are such that this assumption is true. And then we also assume that the variance of the gradient is bounded. So these are pretty standard assumptions on the oracle in the literature. So this biased function evaluation, so this unbiased function evaluation could be made biased, and the analysis would just become a little bit more complicated, but it could be done. And this variance could be relaxed. You can have finite 1 plus epsilon moment, but then the complexities would change accordingly. But these are just not the focus of our paper or our work, right? So given the setting, so let me introduce the method. So it's exactly the same standard stochastic gradient descent. So if you just look at this iteration right here, it's exactly theta k is theta k minus 1 minus gamma k times some gradient, where this gradient is exactly the 0th order gradient evaluated at the point theta k minus 1. So this whole thing is just the what is called as a 0th order stochastic gradient descent algorithm, right? So the only thing is that although we call it as a stochastic gradient descent algorithm in the literature, it's well known that it's just not a descent method. It's not a monotonically decreasing function, and perhaps in the non-convex setting, a more common trick is not to output the final iteration. You have instead a distribution or PMF supported on the number of iterations that you have, so 0, 10, minus 1. And then you randomly generate a number between 0, 10, minus 1 with this corresponding PMF, and then output that particular index, right? So this is again a standard trick for getting oracle complexity results for non-convex stochastic gradient methods. So with this setup, our first main result is the following. So if the parameter gamma k of this algorithm, which is the learning rate, is set in this particular manner, and the tuning parameter nu, so recall that nu is basically going to be there in the gradient, right? So in your 0th order gradient, this is the tuning parameter nu, which multiplies the Gaussian. So it's kind of like the variance of the Gaussian. So if you set that tuning parameter in this particular manner, and then you assume that you have some rough estimate of the true sparsity parameter S. So you have some S star, which is like roughly greater than S. So this is just the initial distance, the distance between your initializer and the minimizer. So then under all these conditions, the total number of function evaluations is basically S hat times log d squared over epsilon to the 4, right? So this result is to be compared with exactly this result here, which is for the non-convex problem in the 0th order setting to obtain an epsilon first order stationary solution without any sparsity assumption, right? So in that case, you would have a d over epsilon to the 4, whereas with the sparsity assumption, we have S hat over epsilon to the 4 if you're ignoring the poly-logarithmic d factor, right? So basically the D is literally replaced by S here, or S hat, right? And the thing to notice here is that we did not make any change to the algorithm to take into account that the problem is having this sparse structure, right? So it is exactly the same zeroth order gradient descent algorithm, except that the learning rate and the new are set in a different way compared to the regular SGD analysis, right? So in a way, zeroth order gradient descent algorithm implicitly kind of adapts to the sparsity in the problem if you can, if you know the knowledge of the sparsity, if you know knowledge of the sparsity parameter, you can set the parameters in this way and get an improved complexity, right? And yeah, so this is something that I just told. No special operation is done to handle sparsity. And one can actually get an improved result in the convex case, as we could expect. And it turns out that in the convex case, you need to truncate the gradient descent iterations. Without this truncation, this phenomenon doesn't occur in the convex setting, right? So you need to truncate this SGD iterates in each round, where this P S hat of theta is nothing but in each round you keep just the top S hat entries, and remaining entries are set to 0, right? So this is the only change. So the rest of the algorithm is the same. You just need to run this standard SGD iteration with truncation, right? So if you do that in the convex setting, if you set your tuning parameter gamma k in this particular manner and your learning rate nu in this particular manner, one could obtain an epsilon optimal solution with oracle complexity of the order of S hat over epsilon squared, where this result is to be compared again with uh, this result here for the convex case, where without any sparsity assumptions, the rate of convergence is, or the oracle complexity is like D over epsilon squared, where D is the dimension. Whereas with this sparsity assumption, if you make this modification to the SGD algorithm, you would have S hat over epsilon squared, ignoring the poly-logarithmic factors, right? So these are the first set of results that we have for reducing the dimension dependency in zeroth order optimization under sparsity assumptions on the objective function being minimized, right? So the next set of assumption is what we call as the manifold assumption. So perhaps before I go to the manifold assumption, let me stop here briefly to take any questions if there is some.
Excuse me, sorry. Maybe I'm not following, but what is capital X?
Oh, the capital X is basically, so if you go to the problem definition, so it's basically the expectation with which you take, I mean, it's the random vector or the randomness with which you take the expectation with respect to. So in a way, you can think of this as if you have an additive noise in your model, when you're observing your f of x with some noise which is additive, this would be like f of x, f of theta plus x. That would be the noise.
But my question may be like, why in following assumption, like you assume that with any query for theta that you can get f theta equals the exact expectation if x is the sampling part.
So I'm just assuming that you observe the noisy function evaluation, right? So here, this noisy evaluation is not an additive noise; it is any general noise.
Oh, okay, I guess. Okay,
right?
Thank you so much.
And here I take an expectation with respect to both the randomness in your noise and the U, and that's when you get an unbiased estimator.
Oh, I see. Thank you. I got it.
Thanks. Any other questions? Right. So if not, let's move on to the manifold setting. So now the problem that we are going to consider is the same zeroth order optimization problem, except that the function little f, or equivalently this capital F, is defined only on a manifold. Right. So it's not defined over the entire Euclidean space. It's defined only over a manifold, which is embedded in RD. Right. So, and again, as usual, the function f is not observed analytically. Only noisy evaluations of the function on the manifold could be obtained. Right. So you can only query the function on the manifold because the function is defined only over the manifold in some sense. Right. And examples, some standard examples of the manifold include the sphere, Stiefel manifold, and manifold of PSD matrices, and so on and so forth. Right. A lot of optimization problems arising in machine learning and statistics could be formulated as Riemannian optimization problems. So let me just briefly highlight one problem which I'm currently working on, where this zeroth order Riemannian optimization techniques are potentially useful. So we know that there are in the last decade or a couple of decades, a lot of geometry-based dimension reduction techniques were proposed in the literature. So in the recent days, more topological dimension reduction based techniques are starting to emerge in some sense. So without going into the details, so there's something called as a persistence diagram of a data set, or a point cloud as they call in this TDA literature, which kind of roughly captures some topological features of your data sample observations. So let's just say d of x means that you have some topological features for the original data set in d dimension, let's say, right, or some p dimension or whatever. And I want to reduce the dimensionality of the data. So this p transpose x is going to reduce the dimensionality of the data and project it onto a lower dimensional space. But then I want this same topological feature, where this d is the persistence diagram again, in this reduced dimensional space to be the same or preserved as much as possible in comparison to the original dimensional data x. Right. So I'm kind of overloading the notation here. Here I mean x to be the whole data set and not just one observation or one random vector, but this is just an illustrative example, right? So how do you measure this similarity between the persistence diagram in the original space and the reduced dimensional space? You just take the Wasserstein 2 distance between those two persistence diagram, right? And now the goal is to find one projection, or find a projection that minimizes this metric, right? And this problem is easier said than done because persistence diagrams are multi-sets. So if you want to define the gradient of this objective function, it's a non-trivial problem to write it down analytically, even what the gradient of this objective function is, right? And even if you can write it down, which one could do, computing it analytically is another story, right? However, what we can do is, like, we can, for a given p, you can easily evaluate, or not easily, but you can relatively easily evaluate this objective function, right? So in conjunction, so now this p is in this Stiefel manifold. So basically, this exactly falls under this Riemannian optimization setting with some effort, right? So there are also other applications in robotics where your constraint sets actually would be like a PSD manifold or orthogonal group or unit sphere and so on and so forth, right? So these are one can kind of see that more such motivating applications of zeroth order Riemannian optimization techniques are going to arise in the near future. One could guess that or make that prediction, right? So what's the issue here, right? So what's the issue that we are going to face? Why can't we just use a regular Euclidean gradient estimator, zeroth order gradient estimator? So recall that, let's again in the non-noisy setting for simplicity, your Euclidean gradient estimator is given by this expression here. So you have f of theta plus nu u minus f of theta over nu times u, where u is a standard Gaussian vector, right? But the point is that in the Riemannian setting, this theta point, although this theta can lie in the manifold, this theta plus nu u, which is the perturbed version of theta, might not lie in the manifold, right? So hence, this function cannot be evaluated at all when this theta plus nu u goes out of the manifold, right? So that's the main issue here. So some care needs to be taken to modify it so that you bring, although it goes outside the manifold, you need to bring it back to the manifold and then evaluate the function on the on that point, right? So that's the rough idea here, right? So before proceeding, unfortunately, we would have to go through some basic definitions of Riemannian optimization. So I'll try to be do this at a high level. If you are curious, you could refer to the paper, or I'd be happy to clarify it later at some point, right? So the tangent space of a manifold of a point theta in a manifold is a linear subspace that contains all the derivatives of differentiable curves of a particular form, which I haven't gone into here. So it's roughly, we know kind of like a sphere, for the sphere, what would be the tangent space. It's just a general version of that definition. And then we assume that this manifold M is equipped with an inner product on the tangent space, which we denote by this curly braces or the rectangular braces. Triangular braces. And the most important concept for us in this talk is something called the dimension of the manifold. We denote by M, this little m, the dimension of the manifold. So what is the dimension? It's basically the dimension of the Euclidean space that the manifold is locally homeomorphic to, right? So roughly speaking, manifolds could be thought of as like locally Euclidean spaces. So what's the dimension of that local Euclidean space that your manifold is homeomorphic to? That's what is called as this dimension of the manifold. And one can show that the dimension of the tangent space is always equal to the dimension of the manifold. This is a fact, right? Just to give you an example, although these things might become like abstract if you haven't seen that before, one can express all these things or calculate all these things for standard examples. So if your manifold is the Stiefel manifold, which we introduced before, which is just the x transpose x equals I, then one can show that the tangent space corresponding to this manifold is given by this expression, and one can calculate the dimension of the manifold to be np minus 1/2 p times p plus 1. So of course, this is always less than np, which is the Euclidean dimension, the original Euclidean dimension of this space, right? And although this example might not give you the benefit of or show that M is much less than NP, there are other manifolds for which the actual Euclidean dimension would be much higher, or the Riemannian dimension would be much less than the Euclidean dimension in which the manifold is embedded in. And the standard example is the low rank manifold. However, things are more a little bit complicated to write down, so I just chose this example here, right? So the bottom line is basically that in general, the dimension of the manifold could be significantly less than the dimension of the Euclidean space in which it is embedded in, right? All right, so we would need to define what is a Riemannian gradient, right? So the general definition of the Riemannian gradient is given in the first bullet point. However, what we can think of because we are working in embedded submanifold setup, all you need to do is that you need to calculate the Euclidean gradient at a particular point, and then basically project it onto the tangent space, and that is what is going to be your Riemannian gradient at that point. So this is the definition. This definition, the general definition, would simplify to this definition when you're working with Euclidean submanifolds, right? And this is good enough for us because we are anyway working inside embedded submanifolds, right? And this projection operation, again, although it might become, or we don't have to think of it as something abstract, it could be analytically written down or calculated for standard manifolds. And for the Stiefel manifold, it's going to look something like this, where Q is A minus A transpose over 2. Right? So bottom line is that all these expressions or all these abstract looking objects could be analytically written down for several standard examples. Right. All right. So one last definition that you need is also the most important thing, which is something called as the retraction map. So roughly speaking, what we need to think of is that retraction map is a map that is going to bring the points on the tangent space back to the manifold, right? So this goes back to our motivation or main issue that we focused here or highlighted here. So when you are doing an addition operation like this in the Riemannian manifold setup, this point may immediately go outside of the manifold. So you need something to pull it back to the manifold. And that expression or that mapping is exactly given by this retraction mapping. And again, although the definition might become or might look abstract, for Stiefel manifold, you have this as a retraction map, and it could be written down analytically, as I told, for several interesting special cases, right? And one thing to keep in mind is that this retraction mapping is not unique. Even for the Stiefel manifold, other maps might be possible, right? So given these definitions, this is a modified Riemannian zeroth order gradient estimator. So in order to do that, we first need to generate a Gaussian random variable or random vector in the tangent space of the manifold. So this is a non-trivial problem for general manifolds. So if you give me a sampler which helps me to, which gives me a point on the tangent space of the manifold, one could immediately, I don't need to make the assumption that the manifold is embedded in an Euclidean space. The only reason why we had to make the assumption that the manifold is embedded in a Euclidean space is because there's no general way to generate Gaussian random variables or random vectors on the tangent space of the manifold. However, when the manifold is an embedded submanifold, there is a simpler way. You can just generate u naught in the Euclidean space. So this has to be a D, sorry. So you can first generate a u in RD, and then use the orthogonal projection matrix onto this tangent space, and that is going to give you a random vector, Gaussian random vector on the tangent space of the manifold, right? So given this, what we have done here is basically, if you recall, this is again the zeroth order Euclidean gradient estimator. So this theta plus nu u doesn't lie in the manifold. So basically, we just use this retraction map here. So at the point theta, we first generate a u on the tangent space, and then bring it back to the manifold. And then basically, this is the only modification that we need to do. Right. So once again, the only reason why we need the submanifold assumption is that it's to my knowledge, it's not explored how one can practically generate Gaussian random vectors lying on the tangent space of general manifolds. Right. All right. So given this modification, we need the equivalent condition for the smoothness assumption that we made in the Euclidean setup. So this is how the smoothness condition is going to look like. It's very similar to the Euclidean smoothness condition, except that there are some subtle differences, which I would not go into for the sake of this talk. Right. So the main properties of the Euclidean the Riemannian gradient estimator is that all your bounds in terms of the bias bound, the variance bound, and so on and so forth, you're just going to have the M in it, and the D would never make an appearance in these bounds. The D is the Euclidean dimension, and M is the Riemannian dimension. So if you recall, for point A, in the Euclidean case, you would have a D plus 3 to the 3/2, which was the first thing I showed in the first few slides. Whereas with this modification, you would only have an M plus 3 to the 3/2, right? So I want to also highlight an alternative way to estimate the Riemannian gradient, which would not lead to this bound. So just to go back to the definition of the Riemannian gradient here. So when the manifold is embedded in Euclidean space, I told you that the gradient of the Riemannian gradient is given by the projection to the tangent space of the Euclidean gradient, right? So one might ask, what if I just estimate the Euclidean gradient first and then project it onto the tangent space? The point is that from basic statistics, we know that this is going to be a functional of a parameter. So whenever you are estimating a functional of a parameter, if the functional is a complicated functional, it's better to directly estimate the functional rather than using some plug-in estimators. So if you do the plug-in estimator as I just described, these bounds would have a D in it, which gains you nothing, right? So that's why we need this modification with which we can get this M here instead of the D, right? All right, any questions before I present the results? All right, so if not, so I introduced the concepts in the non-noisy setting. So in the stochastic or the noisy setting, again, you just have the same thing. You're just going to observe the noise, observe the function values with noise, and you just have this as your stochastic Riemannian gradient estimator, right? And even for this case, similar bias and variance bounds are possible. It's very easy to do that calculation, right? All right, so with this, this is the standard, this is the zeroth order Riemannian stochastic gradient method, which we proposed in our work. So it's again Euclidean, it's again the Riemannian first order stochastic gradient method with the gradient replaced by the zeroth order gradient here. That's the only difference. And you still need to select distribution, have a PMF on the index of the iteration and then generate something randomly, because these are inherently non-convex problems, right? And if you set the tuning parameter or the learning rate in this manner and your smoothing parameter in this manner, your oracle complexity to obtain an epsilon first order stationary solution is given by M over epsilon to the 4. So recall that in the Euclidean case, it was D over epsilon to the 4. Under the sparsity assumption, we had like S log D squared over epsilon to the 4. In the Riemannian case, the D never makes an appearance. It's independent of the ambient Euclidean dimension. It's only dependent on the Riemannian dimension M. That's the benefit here, right? All right. So how much time do I have? Maybe a couple of minutes. Hello? Hi, Michelle.
Yeah.
How much time do you have?
Yeah, I don't know. I just wanted to, I have to go. I have to run, teach now.
Okay.
Very nice talk. Really enjoyed it.
Thanks. Yeah. So maybe I will quickly yeah, just wrap up. So we also have a Hessian estimator here, which is going to look something like this. So you can evaluate the Hessian matrix as well based on function evaluations, which is going to look like this. And we have a version for the Euclidean and also the Riemannian setting. And one could do this in a cubic regularized Newton method. So the cubic regularized Newton method is basically a zeroth order, second order method, which requires both the gradient and the Hessian information. However, one could do the zeroth order estimators of the gradient and the Hessian and plug it into the Newton method, and you can have a zeroth order version of these Newton methods. And with that, one could have an epsilon second order stationary point. So to get to an epsilon second order stationary point, the oracle complexities would be of this order. So this is the Euclidean result, and in the paper we also have the Riemannian result, where this D would just be replaced with a little m, and that would be the corresponding Riemannian version of this result, right? All right, so that's pretty much what I wanted to tell, and if there are any questions, I'd be happy to take it now. Yeah.
Hey, it seems that Ian also have to leave, so.
Oh, okay, no problem.
But, yeah, but thanks for the talk. I mean, I really enjoyed it. I just have a quick question.
Sure.
On the, so it seems that when you're in the manifold case, really, where most time we do not know the projection map to the tangent space. We do not have the tangent space, right?
Yes. So
what do you do in such case? Like this example you mentioned, this persistent homology pursuit. So you're looking for projection matrix there, right? So like in that case, what would you do, for example?
Yeah. So in this case, we do know the manifold is the Stiefel manifold. Yeah. Right. So in this, so unfortunately, or it's if the manifold is unknown, I don't think we first need to find a way to estimate the tangent, the projection map, or some properties related to this manifold, and then use it in this framework or something. But I have not thought deeply about it. For at least this current work, we need to know the manifold and everything about the manifold for it to work.
Yeah. Have you tried? My background is in applied topology, so it's have you tried to use this for this persistent homology base?
Yes. So so I've been working with Wolfgang, who's also an expert in topological data analysis here at UC Davis. So we have been working together on this, and we have some results. So basically, so because these gradients are not easy to calculate even in the first order setting, or have an analytical form for that, there are two ways to go about it. The naive way is just throw everything into like a TensorFlow or something, and it does everything for you through this automatic differentiation and things like that. So, and then the more zeroth order way is like what I just described. So right now, with some effort, we have managed to get similar performance as like autodiff or something like that. And it can detect, for example, in a 3D space, if you have a circle, and then you want to find that there's a circle by projecting on also to the 2D space, it can detect these sort of simple shapes or holes in the data.
Okay, that's cool. Okay.
Yeah, so hopefully this is ongoing work, and I think in a future talk or something I can talk about this more. Yeah.
Okay, great.
I'd be happy to hear.
I would appreciate. I mean, later you have a preprint or something. I'll be happy to read. So
sure. Yeah.
Cool. Okay, this is great. Thank you.
Yeah.
Thanks. Okay. Okay. I think everyone else left, and then thanks again.
Thanks for
I think it's an excellent talk. I enjoyed it
Thank
a lot.
You.
Yeah.
Feel free to reach out if you have any questions. Yeah.
Sure. I would. Okay.
Bye.
Thank you. Bye.
Bye.